Myself, Srinivasan, working as a faculty in the Department of Mechanical Engineering at Sri Shanmugha College of Engineering and Technology. In the last couple of lectures, we have been discussing about RNN. Due to vanishing gradient issue in RNN, and we are supposed to move towards LSTM and GRU. So the LSTM and GRU is a different architectures when compared to RNN. So the basic funda comes from RNN, but it is slightly different architectures. So that we are going to discuss now. If you look at LSTM, it is a recurrent neural network architectures. It is a type of recurrent neural network architectures developed by these two scientists, Hockeiter and Schmidt-Weber, in the year 1997. Okay. So, for example, if you look at these two sentences, and the today is depends on the word. The need depends on the word today. Okay. So there is a long range dependency. Okay. Suppose if you look at this sentence, today, due to my current job situation and family condition, I need to take a loan. So the word need depends on the previous word today. Similarly, if you look at this sentence, okay, and the word had depends on the word last year. Okay, in simple RNN, it can capture the few sequences, but it can't capture the long range dependency. Okay, so to have that, we move towards GRU and LSTM. Okay, suppose if you look at this sentence today, due to all will go into a hidden state. So this hidden state will have many neurons. Okay, this is one neuron. This is another neuron in the state. So it gets the inputs from the it takes the value from the previous hidden state and the current input features. So there is a summation and activation happens over here, and finally it gets predicted. Okay, so it goes to prediction based on the weightage, and there we have summation and activations. So today now here we are looking at the different hidden state as a function of time. Okay, as a function of time, different hidden state as a function of time. So the simple RNN can be named as vanilla RNN, and this is basically we have an input and the corresponding weight will be there, and we have something like the weight associated with the previous hidden state. Okay, so the current one is basically the summation and activation over here. This is summation here and activation. Okay, so we get an output over here, and this information goes to the next hidden state. Okay, so this is the way it works. So basically, what is this HT? HT is basically G of W HT minus 1 plus U of UXT. So this is the input. This is the information from the previous hidden state. Okay, so this is basically, I can say this is a linear combination of vectors. So linear, I can say linear combination of vectors. Okay, so since it is a linear combination of vectors, this G is basically a non-linear function. This is a non-linear function we apply over there. So mostly here a sigmoid activation function, non-linear function. Okay, so this is the way it works for the particular hidden state. Okay, let us talk about before going to talk about the fully gated recurrent unit, we should see what is GRU. GRU is basically it tries to have past memory. Okay, in the previous RNN, if you look at this, and it has the small information comes from the previous hidden state. Okay, that is a usual thing in RNN, because in order to have this long range dependency, we should have memory we should have the memory of past hidden states. Okay, so how it is happening? Because if you look at this is our normal way to calculate HT. There is a activation function, time H is activation function, and this already we discussed. This is a linear combination of the vectors. Okay, So this I can write in terms of G. Okay, G is basically G is equal to tan H. This is ZZ. ZZ is basically a linear combination of vectors. Okay, so this I have slightly simplified the form. Okay, so when you have this, this is basically a simplified form. When you combine this output of that plus older computations, if you look at this one, and G is G 1 minus lambda plus lambda into HT minus 1. So this one takes care of the old one. This one takes care of the new informations, the recent one. Okay, so basically what is this? This is the current one. This is the past one. This is the past information. This is the current one. Okay, so that is the way it calculates. So basically in the lambda is which is scalar value. So whenever we have a lambda is 1, it tries to keep this older memory. Okay, this is a if I put lambda is equal to 1, so we'll have only this term with this, so the current term will not be there. Okay, so then we can say it is going to be purely a memory. Okay, so what is this? And it tries to have small information. It is not exactly memory. It is try to have the small information and the it tries to have the previous it tries to have the previous informations. Okay, so when you put 0 over here, when you put 0 in this case, okay, so it doesn't take care of any past history. Okay, it forgets everything. It tries to compute only the current situations. So then that is the reason it forgot the memory. Okay, so what is the memory here? It that if you look at this one, it's what is the memory here? The previous time steps, that information that it takes it takes into the account of the last computation steps. That's why we used to say here memory. Okay, see, whatever we discussed here is basically a scalar one. In order to have everything we discussed in terms of vectors, so we can write in this way. So if, for example, HT is basically 50 into 1, that is basically the dimension of this. Is a 50 neurons will be there, okay, in the hidden state. So the way we have written in scalar, here we have written in terms of vectors. So 1 minus f, this is a pairwise multiplications. I can say this is Hartmut operations. Basically, if you look at any matrix, and we'll column into row, we'll transpose and we'll multiply that. Here it is going to be a pairwise multiplications that is represented in this way. Okay, it is a pairwise element-wise multiplications. Okay, so this is basically f is basically a vector over here. This is G is basically output of this, and similarly this will take care of the current one. This is take care of the past output. Okay, so f Hartmut operators and HT minus 1. Okay, so when you have this element wise multiplications, and it takes care of this, it cares of the old one. That's why it is called forget kits. So this takes care of the information. It takes care of the controlling the information, I can say. Okay, so this is what it represents. So here we have written scalar, here we have written in the way of scalar, here we have written in terms of vector. Okay, so we used to represent in terms of vectors here. Okay, so that is the way we write. And for the case of f, in place of lambda we put f. The f can be represented as of sigma of our previous one and the current input. So why it is a sigmoid activation function? So what are the values we have? It should be 0 to 1. Okay, it is similar to 1 we used to see in logistic regression. Okay, it is similar to logistic regression. So all the values should be between 0 to 1. Okay, suppose if we put 0 over here, so we will consider only the past one. Okay, if you put 1, if you put 0 here, and what is happening, we don't consider the forget one, we'll consider only the present informations. Okay, so when you have this in between, with the values between, we will take the input from the past one as well as the current one. So that is the way it has been structured. Okay, this is simplest way of representing GRU. Okay. So in the linear, in simplified RNN, we have this linear combination of vectors, and we apply a nonlinear function. So we have the two parameters, the u and w over here, but here it is not the case. Okay. So we have we are in simplified units, we have more parameters. It is going to be double. So I can, I mean, it can be represented in this way. This is our input. We will have a weight, and it will have a previous. If it comes from the previous step, if this comes from the previous step, it will have a associated weights. Okay. So if we compute this is basically a activation function. It is we have a wall. This is also wall. The F is basically a controlled information, because how much we have to keep in the past memory and how much we have to use this present one. So these things can be controlled by a gate. So this is basically a gate. Okay. This is basically a gate. Okay. So if you look at this way, we can control the information, how much we can, information we can give. For example, if I put f is equal to 0, and then it is going to be different. If I put 1, it is going to be different. If I put in between, then it is going to be how much we have to keep from the old one and how much we have to keep from the current informations. So based on that, we can manipulate this. That's why this gate operation is given over here. Okay. This is a case of simplified GRU. Okay, when you look at this fully gated recurrent unit, and this has been developed in the year 2014. In LSTM, it was developed in the year 1997 by these two scientists. So this is basically a slightly modified version of our SRU. So here it is same, but in this case we have added G prime. Okay, so in G prime is basically can be written in this way. So we have added one more gate. Okay, how much amount of information we have to keep. So as I said, this belongs to the old. This belongs to the old old memory, and in that, how much amount of information to be kept to create a new memory. So that is the reason we have put a remember gate or reset gate. So one can say either one of the way, and this is the modification we have done in the case of fully GRU. Okay, so that is the purpose of using GRU. The difference between the GRUs lies between simple RNN and LSTMs. For example, if you look at in RNN, will take care of 20 sequences, and this will take care of 70 sequences. Even if you look at LSTM, will take care of more sequences, because as we see in fully graded networks, we'll have many parameters. Here also this parameter almost 12. Okay, this if you look at in simple RNN, we'll take care of only these two parameters. But in this case, we have many parameters. I mean, we have 6 parameters I can see here. So we have many parameters, and it is for the particular hidden state. If you look at many hidden state, it is going to be more. Okay, so this GRU lies between RNN and LSTM. So in the next lecture, we will look at more of LSTM. Thank you.